Hello guys, welcome back. I am Ranin Sen. So guys, till now we have already discussed about the working operation of a single phase half bridge voltage source inverter with the help of their waveform of different kinds of load like purely resistive load, purely inductive load, and combination of resistive inductive load, etc. So in the similar manner, today we are going to start our discussion with the working operation of a single phase full bridge voltage source inverter. So guys, let us start with the circuit diagram of a single phase full bridge voltage source inverter. So as you can see there, this is the circuit diagram of a single phase full bridge voltage source inverter. Here S1, S2, S3, S1, S2, S3, S4, S4. These are called switches of the full bridge inverter. But in case of inverter, we have generally used thyristor as a switch for the working operation of a full bridge voltage source inverter. Okay. Now D1, D2, D3 and D4 are called a flyback diode. The purpose of flyback diode is to fed back power to the DC source. But in case of purely resistive load, there is no need to use of these flyback diode. But it is only used for inductive load, capacitive load, or combinations of resistive inductive load and etc. So here VDC by 2 is nothing but it is used as a input of the inverter and DC source of the inverter, and the point O is called the midpoint of the DC source, which is connected to the ground, okay, this is ground. Here load is connected. Here it could be anything like purely resistive load, purely inductive load, etc. The polarity of the output is already mentioned, means the polarity of the load is already mentioned. Whatever the load is connected at the output and whatever the current is flowing through that load, that current is represented by I0 here, and whatever the voltage is appearing across the load, that voltage is represented by V0 here. So V0 and I0 is nothing but it is called output voltage and output current. Okay, here VAO and VBO are called pole voltages. What is called pole voltages? The voltage which is appearing across the output point of the leg and midpoint of the DC source, that is called the pole voltages. So let us see the working operation of this inverter for the time duration of 0 to T by 2. For the time duration of 0 to T by 2, switch S1 and S2 is on. So when S1 and S2 is on, the pole voltage VAO must be VDC by 2 and the pole voltage VBO must be minus VDC by 2. Why? Because for the pole voltage of VAO, the point A is connected directly with the positive terminal, and for the pole voltage of VBO, the point B is connected directly negative terminal. So that's why the pole voltage VAO is positive VDC by 2 and the pole voltage VBO is minus VDC by 2. So what about the load voltage at output during the switching operation of S1 and S2? The pole voltage will be the difference between the the output voltage VAB will be the difference between the pole voltage VAO and VBO. So when we are going to put the value of VAO and VBO in terms of VDC, so it will come out to be VDC. Okay, so guys, during the switching operation of S1 and S2, the load, the output voltage appearing across the load is VDC. Now next, when we are going to talk about the switching operation of S3 and S4 for the time duration of T by 2 to T. Okay, so in this case VAO must be minus VDC by 2 and VBO must be plus VDC by 2. Why? Because B, the output point B, is directly connected with the positive terminal and the output point A is directly connected with the negative terminal. So that's why VAO and VBO, VAO must be minus VDC by 2 and VBO must be plus VDC by 2. And what about the output voltage VAB or V0? That will be the difference between the pole voltage VAO minus VBO. When we are going to put the value of the VAO and VBO here, so it will come out to be minus VDC by 2 minus VDC by 2, then it will come out to be minus VDC. So guys, during the switching operation of S3 and S4 for the time duration of T by 2 to T, the output voltage, the voltage which is appearing across the load is minus VDC. Okay, okay guys, let's have a look the quadrant operation of switch and diode of single phase full bridge voltage source inverter. See, we have already defined the value of output voltage during the switching operation of S1 S2, and we also defined the value of output voltage during the operation of S3 S4. So what we observed during the switching operation of S1 S2, during the switching operation of S1 S2 for the time period of 0 to T by 2, the output voltage is plus VDC. In similar manner, during the switching operation of S3 S4 for the time period of T by 2 to T, the output voltage is minus VDC. That two output voltages during the different time period we have already explained. Okay, now let us talk about the load current during the switching operation of S1 S2. See the operation, and let's have a look at the diagram of switching operation of S1 S2 for the time duration of 0 to T by 2. In this case, if current I1 is flowing from the DC source, that will be flow in the same direction of load current. Okay, that will be flow in the same direction of load current. So in this case, the supply current and output current both will follow the same path. So that's why the current I1 is plus I naught, because both the current will follow the same path in the circuit. In similar manner, when we are going to talk about the switching current of S3 and S4, if I2 current is flow from the supply side, that will be flow in the opposite direction of the output current. So in this case, the supply current and output current both will follow the path in opposite direction. So that's why the I2 current, the switching current of S3 and S4 is minus of I0. Why minus sign here? Because in this case the supply current and load current both will follow the opposite path in the circuit, and here I1 is why I1 is equals to I0, because in this case the supply current and load current both will follow the path in same direction. Okay, so that's why in first quadrant, or we can say that the current of the switching operation of S1 and S2 is I1 is I0, and here this current of switching operation of S3 and S4 is minus I0. So S3, in case of S3 S4, in case of switching operation of S3 S4, output voltage and load current, okay, both will come out to be with negative sign. And in the case of in the switching case of S1 S2, both will come out to be, means output voltage and output current both will come out to be with positive sign. That's why S1 S2 and S3 S1 switches provides operation in first and third quadrant. What about the diode D1 and D2? D1 and D2 are nothing but it is called the anti-parallel diode, which is connected in parallel with switches S1. Okay, so the diode D1 D2, it does not change the polarity of the output voltage, but it reverses the current direction. That's why D1 D2 provides operation in second quadrant, and in similar manner D3 and D4 are called anti-parallel diode, which is connected in parallel with the switches S3 and S4. So the function of D3 and D4, it reverses the current direction, but it does not change the polarity of the output voltage of the switching operation of S3 and S4. So that's why D1 D2 diode provides operation in second quadrant, and D3 D4 diode provides operation in fourth quadrant. So these all about the quadrant operation of switch and diode of single phase full bridge voltage source inverter. Okay. Now we will discuss about the waveform of output voltage and output current, means waveform of V0 and I0 in case of purely resistive load. See, here Ig1 and Ig2 are called a gate pulse. Okay, are called a gate pulse, which is generally used for turned on the switch S1 S2 for the time period of 0 to T by 2, and for turned on the switch S3 and S3 S4 for the time period of T by 2 to T. So for the time period of 0 to T by 2, we will get the magnitude of the output voltage is VDC. Okay, and for the time period of t by 2 to t during the switching operation of S3 and S3 S4, we will get the magnitude of the output voltage is minus VDC. Okay, but as we know that the magnitude of the as we know that the waveform of the output voltage and the waveform of the output current will remain same in case of purely resistive load. So when we are going to divide the magnitude of the output voltage by R, then we will get the value of the magnitude of the output current, that is VDC by 4 for the time period of 0 to T by 2, or during the switching operation of S1 and S1 S2, and for the time period of T by 2 to T, we will get the magnitude of the output current is minus VDC by R. Okay, so in case of purely resistive load, the magnitude of the output waveform of the output voltage and waveform of the output current is same, but the difference is that the magnitude of the output current is less as compared to the magnitude of the output voltage. Okay, so this all about the waveform of the output voltage and output current in case of purely resistive load. Okay, let us draw the waveform of the output current in case of purely inductive load and RL load. Before plotting the waveform of output current in case of L load and RL load, first we will plot the waveform of the output voltage with respect to time and output current in case of purely resistive load. I have already explained about the waveform of the output voltage and output current in case of purely resistive load earlier. So here again I will plot the waveform of the output voltage and output current in case of purely resistive load. So for switching operation of S1, S2, S3, S4, S1, S2, S3, S4, S1, S2 like this. So 0 to T by 2, T by 2 to T. The magnitude of the output voltage is VDC. For 0 to T by 2, the magnitude of the output voltage is minus VDC for T by 2 to T. But in case of purely resistive load, the voltage and current will lie in the same phase. So that's why the waveform of the output current is same as the waveform of the output voltage. But the difference is that the magnitude of the output current is less as compared to the magnitude of the output voltage. So here S1, S2 for switching operation of S1, S2, S3, S4. Here VDC by R is the magnitude of the output current, and here minus VDC by R is the magnitude of the output current for switching operation of S3, S4. Okay. Whatever the load is connected at output, the output voltage will remain same in case of any load. Now let us see the waveform of the output current in case of L load. See, the waveform of the output current, we assume that the waveform of the output current in case of inductive load, purely inductive load, is symmetric about T axis. Okay, why we assumed the current is symmetric about T axis? Because at output the DC component is 0. That's why for time period 0 to T by 2 and for T by 2 to T, the current is linearly increases from negative peak current to positive peak current, and for another half period of time the current is linearly decreases from positive peak current to negative peak current. So for 0 to T by 4, and for T by 2 to 3T by 4. For 0 to T by 4, what is the criteria of conducting the diode D1 D2 is the criteria of conducting the diode D1 D2 is the output current should be negative but the output voltage should be positive. So in this region D1 D2 is conducting, because in this region output current is negative but output voltage is positive. And for conducting the switching for conducting the switch S1 S2, the output voltage and output current will both will come out to be with positive sign. So that's why here S1 S2 is conducting. In similar manner, T by 2 to 3T by 4, D3 D4 is conducting, because for conducting the diode D3 D4, the output current should be negative but the output voltage should be positive. The output current, it should be positive but the output voltage should be negative. That's why the diode D3 D4 is conducting for T by 2 to 3T by 4. And for conducting the switch S3 S4, both output voltage and output current will come out to be with the negative sign. That's why S3 S4 is conducting for 3T by 4 to T. Okay. Now the important question is that how can we calculate the value of peak current? See, we know that the voltage is appearing across the inductor is how much? VL is LdI by dt. Is that clear? VL is nothing but VL is the output voltage. Output voltage which is appearing across the inductance load. How much voltage is appearing across the inductive load is, it is VDC. So here VDC for time period 0 to T by 2, the current is changed from positive peak current to minus peak current for time period of T by 2. So here 2IP equals to VDC into T by 2 by L, and IP or peak current will come out to be VDC by 4FL, because as we know that the time period is the reciprocal of the frequency. So this is the expression of peak current in case of purely inductive load. In similar manner, in case of RL load, the current is exponentially increase or exponentially rise from minus IP to plus IP. Here again D1 D2 is conducting for 0 to T by 4, and for T by 4 to T by 2, here S1 S2 is conducting like this. Okay. This is how we plot the waveform of output current in case of L and RL load. Now as we know that the Fourier series of the output voltage of a square wave is summation of n equals to 135 up to infinity 4 VDC of n pi sine n omega t. Okay, this is the most important expression of the Fourier series of output voltage of a square wave. Okay.